restarting our their monthly talks that start and stop and start again, but we're coming to the end of the summer, so hopefully they will be monthly from here on out. So we're going to have a talk today by Professor Xubin Zeng from the University of Arizona. He's one of our collaborators, and he's going to talk about atmosphere, land, ocean, ice interface processes in E3SM. And with that, I'll turn it over to Xubin.
Thank you, Dave. Good morning, everybody. As Dave mentioned, I'm going to talk about interface processes in E3SM based on the work of my team, including Jack, Mike, Peter, myself, in collaboration with a bunch of DOE scientists from PNL, NANO, Lawrence Berkeley, Oak Ridge, and Lawrence Livermore. Because we talk about the interface processes, we will start from below ocean surface, the barrier layer, to above ocean surface, to marine boundary layer clouds, and to the ocean surface, turbulent flux. Then we move to land, talk about land surface parameterization and spin up time, then move to Greenland air temperature, then move back to talk about land atmosphere coupling. Not covered in this presentation is our work related to the SADC project on dynamics physics coupling in E3SM led by Hui Wang from PNL and Carol Woodward from Lawrence Livermore. I'm going to cover each topic with more details for the first two topics. First, the barrier layer. Under normal condition, under ocean surface, we have the mixed layer with the warm water and the cold water below. In contrast, under some special conditions, such as with heavy precipitation, we could have two warm layers. The top layer is warm and fresh, the mixed layer, followed by a warm and salty, the barrier layer, and together these two layers is combined as the thermocline layer. Therefore, we can compute the barrier layer thickness BLT from the thermocline depth TTD minus mixed layer depth MLD. Barrier layer could be important because it insulates the top layer from the exchange with the subsurface, with the cold water below the thermocline, and could also affect the ocean atmosphere exchange and the waves in the ocean. First, I want to briefly mention how do we estimate those quantities. We can compute the thermocline depth based on potential profile in the ocean. In contrast, the fixed layer depth can use the potential density, including both the and the salinity effect. For the observational data, those layers are computed each of the Argo floating buoys, then average over each month. For E3SM and other models, we simply use the monthly mean profile, then compute those quantities. Of course, we have done our own homework in terms of sensitivity test using monthly mean profile versus using individual time profile, then do the average. The mean absolute difference is roughly 4 meters, and this is much smaller than the difference between observations and models. So this does not affect our conclusions. First, I want to show animation here. Shading indicates the ocean temperature anomaly, and black contour salinity. The solid red line is the thermocline depth, red dashed line mixed layer depth, and their difference represents the barrier layer. This is based on the E3SM ocean and sea ice case unknown, so it's not fully coupled. What you can see is the evolution of the seasonal and interannual variability of SST and the salinity, and also the variation of barrier layer. You also see the front or gradient of the salinity over the West to Central Pacific. Now we move to the fully coupled E3SM. Similar animations. See some major differences in terms of barrier layer. There is not much variation over most of the regions. And except for a very far west Pacific and the maritime continent, we see some variation, plus the salinity of ground. That's in contrast to the ocean-only simulations. And in this slide, top panel shows the global climatology of ocean barrier layer from observations. We see the existence of the barrier layers over the tropics and over mid and high latitudes. The bottom panel shows the E3SM fully coupled simulation minus observations. The key point here is E3SM is able to catch the overall global pattern of barrier layer with the existence over tropics and high and some mid latitudes. However, E3SM underestimates the barrier layer thickness over tropics and overestimates and also expand too far southward towards the equator over mid and high latitudes. Here we also show the contours of P minus E, that's precipitation minus evaporation. This gives you the hint the bias in barrier layer might be related to P minus E biases. And then the question is, how much barrier layer bias is contributed by the ocean model? And the top panel, we show the E3SM ocean run minus observation. And then if we compare with the previous slide, we can see the bias overall is smaller over the tropics. In other words, over tropics, ocean is not responsible. The bottom panel shows the difference between E3SM coupled run minus ocean run. And these differences are likely caused by the atmospheric model and of course land model for the runoff or the coupling between the different processes. Next, we can also try to understand the atmosphere's contribution to the bias over tropics. And here we show the mixed layer depth bias versus P minus E bias. The point is, if mixed layer is thicker, then the barrier layer would be shallower because their sum is the thermocline depth, which does not change as much. We see the mixed layer bias is greatest in magnitudes when P minus E is relatively large for E3SM. In contrast, we see for CESM2, the mixed layer bias is larger when P minus E is close to 0 or negative. We can also look at atmospheric model contribution in mid latitudes. As over the tropics, P minus E bias is still important for MLD bias. Furthermore, we also see the dependence of mixed layer depth bias on the wind stress over mid latitudes. In other words, both P minus E and wind stress are important over mid latitudes in terms of their impacts on mixed layer depth bias. Now, the question is the barrier layer important? To quantify its impact, one way is to compute the vertical mixing contribution to temperature tendency of the thermocline layer. And that's shown in shades in this figure. We see its importance. Then we also show the difference in BLT between the coupled and ocean-only simulations, you do see the overlapping between the contours and the colors, indicating, yeah, barrier layer is linked to the temperature tendency of the top layer. Even more directly, we can look at the temperature anomaly versus the barrier layer thickness anomaly. We show the results top left panel from E3SM coupled simulation and bottom left from GFDL real analysis. First, we see the SST anomaly range is pretty nice from E3SM. It's fully consistent with that from GFDL real analysis or from E3SM ocean-only simulation. However, if you look at the BLT anomaly for GFDL real analysis, it varies from around -10 meters to greater than 10 meters. In contrast, for E3SM coupled round, that's top left, we really don't see many points beyond 10 meters. In other words, for E3SM coupled round, PLs rarely get thick enough to cut off entrainments cooling from below, and we feel this might be a potential factor for the negative SST bias over the equatorial Pacific in E3SM. The conclusion for this topic, we are going to submit this manuscript next month to JGR Atmosphere, part of the E3SM special collection. In E3SM coupled round, barrier layers are generally too thin over tropics, while in mid-latitudes they are too thick and extend far equatorwards. Over some tropical regions, barrier layer biases are dominated by atmospheric model biases and couplings. Over mid-latitudes, ocean model also makes a large contribution. More specifically, over tropics, BL is contributed by P-E, while over mid-latitudes, both P-E and wind stress play roles. And BL biases affect the model representation of cold water entrainment from below, and hence affecting the mixing contribution to the temperature tendency. And BL biases related to the model SST variability. And this could be an interesting point, but further work is required to further establish this connection. Before I move to the marine boundary layer, I could stop here briefly if you guys have any questions.
Xubin, this is Luke. Can you hear me?
Yes.
A quick question about the G cases, the ocean ice cases you run. What do you think the role of salinity restoring is and the difference between the coupled and uncoupled?
First, for you guys' information, Luke is one of our co-authors and partners on this study. Luke, we have not paid much attention for this study at this time.
Okay.
Any other questions? Okay, so next, I will move up from below ocean surface to above ocean, the marine boundary layer stratocumulus clouds. This is a very old and very well-known problem in climate modeling. And basically, model performance has been relatively poor, and this has motivated many field experiments throughout the years, and some of the field experiments are listed at the top right panel. And from those field experiments, there are very extensive observations from ship, buoy, airborne, and satellite measurements, as shown for the bottom right for one of the field campaigns, Vocus. campaign. And many papers have also been published, and one of them very well-known paper was by Steve Klein from our DOE colleagues, Lawrence Livermore. And here for the left panel, we show one figure from Kishiro, most recent paper. The point is, in spite of focused studies and field campaigns, model spread in marine boundary layer clouds remains too large. For the bottom panel at the bottom is the observation, and all other panels are from different CMIP5 models. You can see, just look at the slope, the red line. For 3 of the models, even the slope is opposite from observations. So the questions are models really that bad? And despite all the studies and field campaigns, we have not made any progress. That does not seem to be the case. So we want to rethink the evaluation of stratocumulus decks. Traditionally, people usually use the core region, the red box in the figure, to represent the stratocumulus decks. But we see in this simple animation, this so-called core region is not really a fixed region, because there is a seasonal variation of the core of the stratocumulus decks. And even more importantly, we recognize from our other research, for example, if you look at the precipitation evaluation, it's quite possible models can produce not too bad precipitation, but shift the region with precipitation. We feel here is the same situation. Models could produce good stratocumulus clouds, but the region could be shifted for different reasons. So we ask, what's the best way to evaluate the models in order to provide new insights for model physics improvement? And then what are the new insights that such improved model evaluations can provide? For this study, we consider both the core regions in red and the extended region in green box. And this paper was just submitted a couple of weeks ago to JGR Atmosphere, and one of our co-authors is Phil Rash from PNNL. And to make sure we have apple-to-apple comparison, we use the satellite simulator using different satellite data. And then we also use the ERA interim to compute the lower tropospheric stability, LTS, computed as the difference of potential temperature between 700 millibar and 1000 millibar. This figure shows a seasonal mean, no cloud cover for 2 seasons, winter and summer. Top row from observation, then bottom rows from 4 American models, E3SM, GFD LCM3, NCAR-CAM5, and the GIS model E2. What we can see is, say for E3SM, that's the second row. If you compare that with the first row, you see the displacement away from the coasts of the stratocumulus clouds. In contrast, NCAR's CAM5 decks are restricted to near shore, not extending far away. And first, for the right panel, we show the top row, the comparison of different model results versus observation for the core regions for each of the 5 stratocumulus regions. If you just look at NEP for DJF, what we are showing here is for core regions, we compute the percentage of grid boxes with no clouds cover LCC greater than 45%. From observation for the core region, the percentage is around 90. That's why the core region is selected. Then for E3SM, it's just about 40%. In contrast, on CAM5, only 20%, even worse. And for CM3 and the model E2, essentially 0. We see that's why core region is not the best idea for the comparison, because models simply displace the stratocumulus regions. Then we also see the differences between models over core regions are pretty large. For this case, between 0 and 40, if you go to some other regions, other seasons, the difference could be as large as 80%. If we do the same analysis, but go to the extended regions as shown in the second row for the red panel, then the overall agreement between models and the observation are better. In other words, model simulation of stratocumulus clouds is not too bad, except the region has been displaced. We can look at the same issue from different angle. Now, for the top panel, we show the climatology of the seasonal cycle from 3 different data sets indicated by the points, say the cross for satellite simulator data, and the circle from ESCAPE D2, and the triangle from in situ measurements over core regions. Even these 3 observational data sets show fairly large differences. And also models show large differences. In contrast, if we go to the bottom row, the extended regions, observational data agree with each other better, model results agree with each other better, and model results also agree with observation better, except this model E2. That model simply does not have much stratocumulus cloud. And now we can move on to evaluate different relationships in the model. Here we show LCC versus lower troposphere stratification. Here we just show the slope between the core regions and the extended regions, and the LCC 45 plus stack means agrees in the extended region with LCC greater than 45%. And if we compare the results over both regions, we see the decrease of the slope from core regions to LCC 45 plus from observation. That's Calypso GeoCCP. And we see E3SM performs best. First, quite close to observations for each region, and second, the change. In contrast, for example, for CAM5, the slope is way too small over LCC 45 plus, while for GFDL is even worse because we see the increase of the slope from core region to LCC 45 plus opposite to the observed relationship. And then next, we want to move further to gain some new insights. So here we show the relationship between LCC and LTS for El Nino versus La Nina periods. For the top row, that's observation. We see the variation in LTS in terms of x-axis for El Nino versus La Nina years. That's reasonable. In contrast, if we look at the E3SM, there is no change in LTS. In other words, the LTS is not sensitive to El Nino versus La Nina events, in contrast to the observed sensitivity. Besides clouds, we also look at the liquid water path. Again, based on our prior experience, realizing in the model, not like the real world, sometimes we may not treat LWP versus cloud cover consistently. Here top, we show liquid water path versus LTS. We see the overall decrease of liquid water path with the increase in LTS from observation, the black circle. In contrast, for other models, we see the near constant or increase with LTS, which is quite different from observations. And here observations are from MODIS. Bottom row, we show LWP versus LCC. And from MODIS, results are nearly constant. In contrast, model results are more sensitive. between LWP and LCC, again, quite different from observations. This kind of analysis would help us to improve the cloud parameterization, particularly the relationship between LWP and environmental conditions, both LTS and cloud fraction. And finally, because so far we have used the E3SM AMIP run, that's atmospheric simulation, we want to make sure results are also applicable to the historical ocean atmosphere fully coupled runs. So here we show the results from E3SM red dot for the core region, that's AMIP run, and the green is for the LCC 45 plus decks from AMIP run, and then the other circle is from historical fully coupled E3SM. Overall results are quite similar for the relationship between LCC and LTS between AMIP and the coupled runs, except over NEP, we see some differences. And in summary, model spread is reduced when considering the extended regions or LCC 45 plus decks. This means for the future, we should probably focus on the evaluation of stratocumulus clouds over extended regions, because if you just focus on the core region, you are going to draw a somewhat misleading conclusions about the model treatment of stratocumulus clouds, because those clouds are displaced. Second, despite the displacement of the stratocu deck, E3SM produces a reasonably good stratocumulus deck. Finally, models displacement of stratocu deck is likely caused by the interaction between model physics and large-scale dynamics. So it's not just a model physics problem. We have to pay more attention to the interaction between model physics and large-scale dynamics. And the second, LTS range from E3SM and the other US models are insensitive to ENSO, contrast to the sensitivity from observations. This is likely caused by errors in the large-scale dynamics, because LTS, the inversions in the atmosphere, largely driven by the subsidence in the atmosphere. Second, model liquid water path is lower than MODIS, sensitive to LETS than MODIS, and much more strongly dependent on LCC than MODIS. This is likely caused by model physics errors. And finally, LCC 45 plus decks are similarly simulated by the historical runs versus in the AMIP runs, except in the NEP. I will stop here if you have any questions on this portion of the talk. Okay, I will move on to talk about some other topics briefly. Now we come below ocean to above ocean and compact ocean surface. Here we show the difference in the annual mean latent heat flux between our turbulence scheme and the default turbulence scheme in the E3SM. The motivation for this study is from our earlier research. We realized the turbulence scheme in the NCAR model, and then now in the E3SM, some deficiencies under very stable conditions and under downwind conditions. That's why we did the implementation of our own scheme to try to look at the potential impact on E3SM modeling. Our scheme was also implemented in the NCEP operational model, and this work is in partnership with Ponen Ma from PNNL. Next, we have also look at other differences between our turbulence scheme and the default simulations. Here in the figure, we show the 5-year annual mean precipitation rates. We see pretty large differences over the Western Pacific, Maritime continent, and the Indian Ocean. We have also looked at other variables. We do see the change in hydrologic surface winds and net heat flux at both surface and the top of the atmosphere. This means if we implement this scheme, we might need to retune E3SM slightly for use in non-coupled model runs, and this will be a E3SM version 2 effort. Next, finally, we move from ocean to land to talk about land model parameterization and spin-up time. And first, I just try to mention we have prepared variable soil thickness over elevation classes in collaboration with Bill Riley and Gautam Bishit at Lawrence, Berkeley. This work has been largely done. We have also developed the downscaling methods from atmospheric grid to subgrid elevation classes for temperature, humidity, downward radiation, and surface pressure in collaborations with Techno Tesfa and Peter Thornton, Techno from PNL and Peter Thornton from Oak Ridge. And as an example, here we compare 3 methods. Our new methods for the downscaling from atmospheric model grids, mean variable, to subgrid elevation classes. Here we use the NASA 7-kilometer GEOS-5 nature run to do the test. Basically, we take the GEOS-5 nature run of the tools test different downscaling methods. We compare our methods. I'm not going to talk about our methods here. I just try to tell you the performance versus the default, the null method. That's a lazy person's method. You do nothing. You just use the grid mean, then apply to each tile or elevation class. Then versus the ice heat method, because in the current E3SM, there is a downscaling methods over ice heat only. So we compare 3 methods over North America. And for 2-meter air temperature, you can see the scattering is much smaller compared with the null methods. The Perlman's methods is also much better than the current downscaling methods used in E3SM ice heat. If you look at the downward non-wave radiation, similar conclusions can be drawn. Basically, our methods are simply better, much better than the null hypothesis of using the grid mean, and also better than the current methods used over ice heat in E3SM. To test its impact, we run the ice heat model, or actually not ice heat model, just land model with ice heat. And for the left column on the default model simulation of the temperature seasonal cycle over 2 elevation bands. And the right column shows the results. Our new results, what you see is, for example, for the top row, the seasonal cycle could be similar. Surprisingly, we see the overall decrease of the surface temperature using our new downscaling method. This is a good news because I'm going to show later there is a mean bias in the E3SM simulation over Greenland.
We follow the NOAA Research and Development Funnel. So business model, if you're familiar with this, where you have more general research and development all the way down into the operational system. We are somewhere, starting where the mission research starts, and also the
sounds like Jiafu Mao is not muted.
Systems for operational capabilities and applications.
Yes. Oh, okay, so
we work quite hard to complement the funding that's out there with engagement and communication and coordination.
Muted.
Okay.
Unmuted.
Here. Oh, geez. Can you guys hear me?
Yes. Can you hear me?
Thank you. Okay. The left panel, we show the spin-up time over Amazon for each of the 15 soil layers. You see, it takes something like 60, 70 years to reach the quasi-equilibrium because of the use of cold starts of constant near freezing temperature in the land model. Imagine this is just a soil temperature. If you talk about land model with the full dynamics and biogeochemistry, spin-up becomes an even more serious issue. And our simple suggestion is, instead of doing a constant near freezing temperature for the cold starts, it's much better to use the annual average 2-meter air temperature or the initial deep layer soil temperature, then do the spin up, and the results are shown in the right panel, and we see the much faster convergence time. This could become even more important again if we consider biogeochemistry and dynamic vegetation. And we have not done anything further, but I mean, if the land team feel we can collaborate, announce this line further, of course, we'll be very happy to help. And next, I move on to Greenland temperature. Last year, we published a paper on Greenland's air temperature, and actually our university released a news story. And here we use the recognized best data from that study. That means that this global temperature plus Mercator's real analysis to evaluate the E3SM temperature over Greenland. Here we have to emphasize, when you do this kind of comparison, you must do elevation adjustment in the comparison. Actually, the right panel, the left panel is a direct comparison showing the bias of E3SM without elevation correction. You see pretty large biases, but once you do the elevation correction, results are showing over the right panel. Results are pretty decent. And again, as I mentioned earlier, if we use our downscaling methods from atmospheric grids to elevation class, we can potentially further reduce the positive bias over northern Greenland. And in this figure, we compare the E3SM historic runs, as shown in the golden color, versus the CMIP5 ensemble mean, the dashed line, and observation, the black line. A positive surprise to me is E3SM can actually catch, to a certain degree, the multi-decadal variability, including the decrease of temperature of Greenland in the early 20th century. That's quite positive. Next, we show the actual temperature after elevation adjustments. Here, we see the E3SM results. The temperature over Greenland is on the warm side of the CMIP5 ensemble, and on average is about 4° warmer on this observational data. And this is the important issue. I hope the ice sheets colleagues could pay more attention, because the 4° mean bias over Greenland will have consequences in terms of surface mass balance in the long run. And finally, I want to briefly talk about our most recent work on soil moisture impact on afternoon precipitation. We just published this paper actually this month. University released a news story plus a TV interview of the students Josh Welty and myself. And again, this is a very old problem with contradicting results in terms of the morning soil moisture effects on afternoon precipitation. And here is a summary of our primary results. Using data from 11 years in the warm season means on June, July, August, and September. If we look at the relationship between afternoon precipitation versus soil moisture, using all available data, the results are shown in the top left panel, panel A, the correlation 0. However, if we use large-scale atmospheric circulation as the important parameter to control the study, here we use the large-scale convergence. Then we divide all the days into 3 regimes. The low regime means large-scale convergence is weak, and high regime with strong large-scale advection of water vapor from the Gulf of Mexico. Then for low regime, that's panel B, we see the decrease of precipitation with the increase of soil moisture. It's quite interesting. In contrast, for high regime, we see the increase of precipitation with the increase of soil moisture. Next, we want to understand the potential physical pathways between soil moisture and precipitation. So, besides soil moisture, we also look at the soil temperature, air temperature, humidity, relative humidity, net radiation, convective triggering potential, low-level humidity index, CAPE, PBL height versus lifting condensation level, and evaporation fraction. We looked at all those quantities, then link them to the afternoon precipitation, and we found under low regime, the thermal forcing is the most important because the stronger the thermal forcing, the better potential for the path from near surface go higher and then reach the level of LCL, then condensed, form clouds, and given precipitation. So we see the positive correlations with soil temperature, air temperature, specific humidity, CAPE, and PBL height versus LCL. We also see the negative correlation with soil moisture. Under high regime, however, we only see the positive correlations with evaporation fraction and soil moisture. And in summary, first, I have already provided the summaries for the first 2 topics. For the remaining 4 topics, for ocean surface turbulence, our work is ready for further testing in version 2. And for non-model parameterization and spin-up time, variable soil thickness is ready for V2. Downscaling for elevation classes are ready for further testing in V2. We also suggest a simple approach for non-model spin-up. For Greenland temperature, E3SM is able to produce the multi-decadal temperature variability. That's very nice, but it has a 4 degrees Celsius positive bias, and this is important to address if we consider the surface mass balance over Greenland. And for soil moisture precipitation interactions, it provides the basis for our near future global data analysis and model evaluation on the precipitation diurnal cycle. I will stop here for any questions.
Hi, Xubin. This is Chris. I had a follow-up question regarding the ocean surface turbulence parameterization you were suggesting.
Okay.
So you show one figure of the change in precipitation. It looked like it was significantly increasing double ITCZ. You remember, you mentioned you need to retune. Did you remember? Because you have drying and then more precipitation north and south of the equator there?
No, I mean, actually, if you look at the South Pacific, we reduce the precipitation and hence reduce the double ITCZ.
So is it, when you evaluate it, was the precipitation better, you think?
Yeah, precipitation is a benefit.
Precipitation was a benefit?
Yeah.
And then what were the drawbacks?
We don't see any real drawbacks, but we do not want to draw strong conclusion because we only did a 5-year simulation. So overall, I would say positive impacts, but over most of the regions, the impact is not big. And for model testing, it's actually it's good.
Are the results available on Confluence?
I don't remember at this time.
Okay. Then if I can, I had another question regarding the stratocumulus. So I think you made a good argument that maybe some of the biases we see is regarding to the shift. And I was wondering if that argument also carries over somewhat to the biases in the large biases we see in shortwave cloud forcing, or is the shortwave cloud forcing bias more related to the liquid water path problem that you also mentioned?
I agree with you, yes. So the point is, I mean, people use the core region, okay, nothing wrong, but if our purpose is to understand model physics, we feel it's important to use the extended region. And it turns out we see the progress in the model physics. The real key now to me, as a model developer myself, is the interaction between model physics and the dynamics, rather than just focusing on model physics. And we did not show any results related to cloud relative forcing. And I agree with what you said. A major bias in the cloud relative forcing, if you look at the fixed region, say the core region, is due to the shift rather than the poor model physics parameterization.
So maybe it would be interesting to see the same analysis of core region versus your extended region for the cloud radiative forcing.
Yeah, we'll do that. Mike is next to me, and Mike just nods. He will do that. Thank you.
Okay, thank you, Xubin.
Any other questions?
Xubin, this is Luke. A couple questions about the ocean surface flux parameterization. Just to be clear, this isn't really touching the ocean physics, right? This is the coupler surface fluxes you're changing?
Yes, the so-called bulk algorithm from the atmosphere side, not from the ocean side.
Okay. So the other question was, are you planning to explore the influence of skin temperature on the fluxes on the ocean side?
You know, of course, we could work on that one as well. Basically, our attitude is, I regard our group as the go-to team for interface processes. If you guys, the core team for E3SM within DOE, feel something is important, and if we have the experience, we will do it. And particularly that might become even more important because, as you know, in the E3SM, I believe the first layer in the ocean, you switch back to 10 meters, right? I mean, in the version 0, you guys at Nano try different vertical resolutions, but in the end, switch back to 10 meters. Is that right?
That's for low res, that's correct.
Yeah, I mean, say for that case, it becomes even more important to have the skin temperature diurnal cycle that provides the good diurnal cycle simulation with minimal computational cost.
Right.
Any other questions?
Xubin, this is Dorothy. Do we know why the temperature over Greenland is too warm?
No, we have not gone that deep. And okay, I don't know. At least, I mean, from our own research, surprisingly, when we look at our new downscaling methods that help reduce the temperature over northern parts of Greenland, who knows? Probably everything is not too bad there on the atmospheric sides if we try the different downscaling approach that could reduce the barriers. Again, we have not done much along that front, and I hope some of the DOE colleagues will be happy to work with us to do that testing, not for the offline testing we have done, but do the coupled testing.
Hi, Dorothy. This is Steve. Wu Yin and some of his colleagues have been looking into this too, and we actually have a call after this call to start looking at some of the cryosphere-related analysis in the atmosphere that they've been doing. So we'll certainly keep people posted as we learn about that. But I don't think we have anything to add right now, but we are looking into it.
Okay, so one point from our last year's paper is that be careful about what data you use for the evaluation. Turns out over Greenland, some of the so-called observational data is as bad as models. Okay, so if you use a different data sets, and you could draw misleading conclusions. And from that paper, again, the GIS temperature data plus MERA2 real analysis provides the best data set based on our analysis. And if you guys need our assistance in providing the data or do some analysis, we'll be very happy to do that.
Okay, thank you. We'll make sure to talk with Wu Yin about that as well.
Okay.
Xubin, this is Hailong. I have a quick question related to that too. Is that unique to Greenland, or did you look at other locations in Arctic or the Antarctic? The temperature bias.
We are analyzing E3SM results over high latitudes, but I did not show any results yet. I just highlight Greenland because we published that paper last year. We thought we have everything ready, and then we can also compare E3SM with all the CMIP5 models because we done those analyses last year already. That's why. We have done other analyses over high latitudes, but I did not show any results today.
All right, thank you.
So Dave, looks like no more questions. I return to you.
Dave's on mute.
So that's all.
Thank you, Xubin.
You are welcome.
So I hope that, this gave people in E3SM an opportunity to